direction here. Yes? What is W, please? Should be unit vector, right? Yes or no? Take any point x here, any point here, x. I want to do the orthogonal, this one. This one will be my y1. How to get the value of this one, please? Is W transpose times x. This is single x, right? I call it x1. If I want to do all the data set, what will be? Y W2 times x1 until x. This time this is the first y1. This time this y2. So what will be at the end? y1 until y n. Done. Clear? So here what we are trying to do. Okay. So we have the mean of the value, of course, here. So if y here, if you do the mean, it will be the same thing. So the mean in y, it is the same thing as the mean in x. But of course, you have to multiply it by the conjugate. So what will be here? If the mean is here, if this one is the mean on x, right? What will be the here? The same thing. It will be the mean times w. Same thing. Any vector on in here, to put it down, just you need to multiply it by the transpose of your vector. We did it many times, right? Okay? So look at example here. Here you have the mean of the red one is mu1. The mean of the blue one is mu2, or vice versa, doesn't matter. So you have to multiply it here to do the projection. You have to multiply it here to get the projection. We call it m1 and m2. So mu1 and mu2 are the origin mean. If we do the projection, we call it m1 and m2. So here it's better to call it, for example, here mu1. If we do the projection, what will be here, please? m1. If we have another for class 2, mu2 is here, what will be here is m2. So what we want to do later on, m1 minus m2 should be a maximum. We have the mean after the projections. Here, the two means is somewhere. You project them, you get m1 and m2. Okay? So, x-axis here, what you want to do? The variance should be, for the class 1, what you want to do class 1? The variance should be minimum. So what is the variance here? y1, the mean of y1. So what does mean, what is y1 is? This, right?
Yes.
Remember, we have to do minus the mean. You put the transpose, and we do the same thing as we get found. So here, the variance is always related to the covariance matrix. So this one I want to minimize. The same thing I do for the class 2. Okay? And of course, we know how to calculate the covariance matrix, right? If I give you data, how to calculate the covariance matrix? By this formula, right? Okay? And the class. So we have sigma 1, sigma 2. We calculate the covariance matrix, but we want to minimize those two things. Okay? So I'm just giving the idea. So look at what we have. We have m1 and we have m2, right? Clear? What we want to do? m1 minus m2 squared should be maximum. What is m1 minus m2 squared, please? How to calculate, please? Look at m1 minus m2 squared. What does it mean? Let's go to the matrix product. What is it, please? Okay, first of all, what is m1 minus m2? Wt mu1 minus Wt mu2. Square, right?
Yeah.
Yes or no?
Yeah.
Okay. What is square? If you want to do it as a matrix product, this one itself times the transpose. But since this one is a value, doesn't matter you put transpose the first or the second. But if it's vector, if it's column, here, x is column. Which will be the, if you want to find the value? xt, x, right? But if x is a row, what will be here, please? xt. It depends on what we are. If x is a value, you put xt, x, or x, xt, doesn't matter, it's cheap. because it's a value at the end. Clear? Is clear this point? Okay. Look it. I try to write this one in a different way. So what will be here, please? Wt mu1 minus Wt mu2. Let's do the transpose. What will be here, please? Mu1 transpose W minus mu2 transpose W. Okay, I remove. Okay, can you write this one nicely? Any idea? Look it. This is common factor. Can you take it outside? But what is the side? What will be? It's important the side. What will be here? Wt times mu1 minus mu2. Here again. This and this. Can you take it outside?
Yes.
So what will be here? Mu1 minus mu2 T, or I can put it all T and W. What will be this one? I will call it the matrix B. Okay? This is matrix B. What we call the matrix B? Between classes scaters. So this one between classes, I want to maximize it. Clear now?
Yes.
Okay. For example, if you have x1, you have x2, you can calculate the mean, sum of them, me2, you can calculate your matrix directly. Clear the idea? Okay, let's go to the values. What is the values of the one protected here? Is Wt sigma 1 plus W2 sigma 2. Here I just multiply by, because sigma 1, when we do the calculations, is always we do 1 out of n, something. I just remove this 1 out of n and care about the difference square. So what will be at the end? S1 plus S2, we take W, so it will be the new covariance matrix between the two classes. We call it capital S. So what is capital S? Is the covariance matrix for the first one plus covariance matrix of second one. That's all, nothing else. But of course you have to multiply by N1 and N2. You see here, for example, here, S1 is N1 times the covariance matrix. S2 is N covariance matrix. You add them, you get a new matrix S. So this is S. What we want to do for it? Maximize or minimize? Minimizing. Okay. So please, you want to maximize something and we want to minimize something. How to put it in nice equations, in one single equation?
Ratio between them.
Okay. Let's do it here. We want to find a minimum of what? S of this one, right? We want to maximize what? Correct? How to put it in a nice form?
Max the ratio between them.
Yes, this is one idea. Excellent. So if you're looking for the max, for example, what we do here?
The max of
WTBW over. Yes, this is one. Another idea.
Put it on constraint. For
We can use or. This we want to maximize, right? Times 1 minus. You see, if you want to maximize this one, you have to minimize this one. Some idea, okay? Whatever you want to put it, which one is the best. But most LDA, they use this one, okay? Because if you want to maximize the ratio, so you have to maximize the numerator and minimize the denominator. Clear the idea? So this is, I have to put it in nice way. So what we call this one? Within the class, minimize. Okay, between the class, maximize. Okay? And we're getting this one to, here I put other things up to you. But let me just try to, as we did in chapter one, let's try to find how we can find a maximum of these functions. Okay? So try to follow me. It's like exercise to the chapter 1, the matrix derivative. Okay, so we want to maximize this one. Okay, So can we do the derivative here? What is our variable, please? What we are looking for?
W.
W, right? For sure, please. Okay. Let's do here the derivative. What is the derivative of the ratio, please? In calculus? Derivative of f of g, what is it? F prime g minus f g prime over
G squared.
g square, right? Okay, let's do it here. What will be here? Numerator, I will not touch it, the same thing. It will be derivative of the first one times the second one, right? Minus times the derivative of the no, here is b, sorry. B s. Is it correct? Yes? Yes or no? Okay. What is the derivative of this one here? We have two with the red one. Yeah. We have two variables, right? The product between two variables. As we did chapter 1, what we do? We do derivative of the first, after we do derivative of the second. Or you can change the order, right? So what will be here, please? If we do derivative of this one, what we have? WTB plus. If we do derivative of this one, we have to do transpose of this one, right? Times minus, please, again here. What is the derivative of this one, please? If we do on the first one, what will be itself minus, if we do of this one, SW all transpose, okay? Now we can just simplify. This and this are the same or not?
Yes.
Think before. Okay, matrix S and matrix B, are they symmetric or not? What is covariance? It's always symmetric. So both of them are symmetric. So let me write this one. This one will be here, please. It will be WTB plus W2B. But B or B transpose are the same. So which we can write it, please? 2 times, yes? Yes or no? So it will be 2 times minus. So this is just extra I'm giving to you. So if you want, no need to, but it's good to understand. Here the same thing, what will be here? 2. Yes or no? And this one I have to put it equals to what? To 0, right? Derivative equals to 0. So what we have at the end? Because if you want to improve this one in your research, you have to do this type of derivative. You can find better objective function to maximize or to minimize, and here you can do some improvement. Okay, so it will be here at the end. Okay, here. So we can simplify the 2 together, right? So what will be here, please? WTB times, this is S, right? SW equals to what, please? Times S, right? Can we simplify here? W, look at please. W with itself equals to what? It is 1 because it is the unit vector. But the unit vector, it is like this. This is equals to 1, right?
Yes.
But if you do the opposite, it will be identity matrix. You can check it. Okay? So what will be at the end here, please? Did I did no mistakes here? Yes. Okay, so here what should be here? SB, and here the same thing is SB. W, right? Look here, please. This is a number or not? This one here. WTSW. No, it is not one, but it is a value or matrix, row or column. What do you think?
The scalar.
It is a value, yes, exactly, a value, thank you. So this is a vector, right? Okay, so here what we have here, this is a matrix times a vector. So what we can find out that BS, it is a matrix of, so BS times this one, it is parallel to BW. Is it clear or a little bit confusing? Okay, so until here, is it clear those steps here?
Doctor,
Yes?
here we put it subject to the equals one, not in the slides.
Here, right?
No, in the slides. Maximize the.
This is,
subject to one.
I'm coming to it, yeah, this is, let me just do it, this one quickly. Look here, for example here, what they say, another way of doing things, but I prefer this one here. Look here, if you take here W, or you multiply by alpha W, doesn't matter, right?
So at the end of the day, we multiply by 0. So this.
Yeah. No, but zero. To make it
I mean, here,
unison.
if we keep the denominator here.
This one?
Yeah. So if we,
Why zero?
I mean we maximize this ratio, right?
Yes.
So it's
But this one we maximize the ratio.
yeah.
To maximize the ratio, we have to maximize numerator and minimize the denominator.
Yeah.
So according to this one, when we do the derivative, we find this one, and this one we have to force it to be zero. But at the end, maybe it's the max for this, or maybe a minimum of this. Because when derivative equals to zero, we call it critical point. And critical point, what does it mean? Maybe max, maybe the minimum, or maybe saddle point. So we don't know. We have to investigate more. But at least you have to find the derivative equals to zero. So let me explain this one and come back to this. Look here, please. Here, we notice here, we're looking for W. You put a W or you put alpha W, the ratio still the same, because alpha and alpha will be simplified from numerator to denominator. So here what we do, we try to use W, any length, in order to force this one to be 1. To force this one equals to 1 means subject to this one. What does it mean subject equals to 1? When you have optimization and you have to do constraint, do you remember Lagrangian parameter? Lagrange parameters?
Yes.
Lambda, yeah. So it comes from technique of optimizations. Okay? So you can use it as it is. Or I give it to you quickly. I come back to this one, okay? Let me do a quick revision about optimizations, please. So when you have optimization and you want to find a maximum or minimum of any functions, what do you need to do, please? So in multivariable we call it gradient, right? As we did. So the gradient should be equals to 0. But now sometimes I give you a function you want to maximize, but I give you a constant equations. That's, for example, here x and y, but I give you x plus y minus 2 should be equals to 0. You have to find this condition. Like, for example, here we have here should be equals to 1. How you will do it? You just modify your functions f of xy. You got minus lambda. This is the Lagrangian, and you put your equation like this. So what does it mean here? Usually, if we satisfy the conditions, when you put it here, it became 0. But to get it, you have to do the gradient of this. You got the idea? So what will be here? If we do here, for example, what is this one here? B W minus lambda. What is the constant here? SW minus 1, right? If we do the derivative, we can find the last equation. What is the derivative of this one, as we did just now? WTB times 2 minus lambda, the same thing here, 2 WTS should be equals to 0, right? So what does it mean at the end? WTB should be equals to lambda WTS. Put the transport to the both sides to make it easier. It will be BW equals to lambda SW, right? Clear? I put the, supposedly that S has an inverse. What will be here? S minus 1, S minus 1, what will be here? S minus 1, B, W equals to lambda W. So this is a matrix. So W is eigenvector of this matrix. That's all. So the W is, at the end, the direction that we are looking for, it is the eigenvalue of S minus 1, P. They are in the slide here, I'm coming to it. So you see the idea here, it's just optimization technique. So this is, I don't want to do it because it's Lagrangian thing. It's not very complicated, but it's good to have an idea about it.
Doctor, in the previous solution you said that W of CW is equal to 1, right?
Yeah.
But here you did not put W.
But where is the WW1? This is S, sorry.
No, here, on the right side.
Here,
In the next skip.
here, so look at.
No, on the right, in the last skip, on the right.
Okay, let me try to slow. Okay, until here is okay?
Yeah.
Until here, I put
Yes.
my equations.
Okay.
Here, I do the derivative.
No.
Okay, just a second. Here is okay?
Yes.
Okay, so this equals to 0. Lambda
I mean
2.
the W T dW. So as a W T W is equal to 1, so it should be only B. But you have to put it 2 W T.
Yeah, because when you do the derivative of this one, you get this. It comes from some derivative, not from WWT. When you do the derivative of this one, as we did in chapter 0, as we did here, is the derivative of matrices. Because this is like x squared. When you do the derivative of x squared, what we have? 2x. Something similar to it. If not, I can give you how we do it, okay? Okay, I will redo it again. This is my, what I'm doing here in the slide, okay? You have the function j. I want to maximize this one. How to maximize this one? We do the derivative of the ratio rule. Ratio rule is this one. Agree for all? Now, how we do the derivative of this? How we do the derivative of this? Okay, we apply the formula. So this, when you do derivative, means this one equals to this one. Now I will do the calculations. Here, the derivative of this one is this. Derivative of this one is this here. And here what we can consider here, please. Look here, this is a value or not? Here, please, always is a value. This one is a value, right? So value doesn't matter. So what does it mean? BW equals to SW times a constant. So please tell me yes or no. This is really, let me give 2 minutes here to stop. Tell me yes or no. Look here, please. When I say here, WT, SW is always belongs to R. What does it mean? R is real value. Clear? Here the same thing. WT, BW belongs to R, right? So what we have in these equations here, after the derivative, what we have here, okay, BW times clear? So please, this one here, this one, I will remove it and put it down because it is a number. Otherwise, I cannot put it for matrices. Yes? Clear? This one, let me call it as any number. Call it gamma, for example. So what we have here? BW equals to SW times gamma. I put down S minus 1, what will be here? S minus 1, BW equals to. So what does it mean here, please? Mean W is eigenvector for this one. And gamma is the eigenvalue. So let me call it lambda better to make it easier. This is lambda, and this is my lambda. You see here? So how to find solutions? it is not always obvious when we have matrices to find the critical point. So now what is our conclusion? We are looking for the best directions. So the best direction is the eigenvector for S minus 1b. But we still have problem. When we do the eigenvalue, we have a lot, right? Which one you have to select? The
one that maximizes them.
The maximus. Why the maximus? Because this one, if I put it in the main equations, you will find it equals to lambda. So we have to find the eigenvector corresponding to the maximum lambda. You see the way how it works now? Let me put it here back. If I put it back here in our function, what we get? Lambda. So we have to find the eigenvalue corresponding to the maximum lambda. What we call it? Principal eigenvectors. As we did before in the PCA. You see, it's always coming back to the matrices. When we deal with matrices in the linear way, we are always dealing with eigenvalue and eigenvector. It comes alone when you do the derivative of it. Okay? Look at it. So here, what we need to do now to find the best directions according to our calculation, you need only to calculate S minus 1b matrix and find the eigenvalue and eigenvectors. And we are done. Look, for example, I have x1 and x2. You have to find the mean of each one, right? And you do this calculation, you will get your b. Why we did these calculations? We want to maximize the difference between mu1 and mu2. We have to find the covariance matrix for the first one, covariance matrix for the second one. We add them and we want to have their minimum values. What does mean minimum values? Means is?
The variance between each class is minimum.
Yes, exactly. Because this one here mean the eigenvector, eigenvalue for capital S should be smallest possible, because it will be really tight. Okay. So we calculate S, we calculate B. For example, here we have two. This is our eigenvector, and this is our eigenvalue. So what is your best directions? Is the one corresponding to lambda 1. So it should be the first one. So what is the first one here? You have to do the projection of your data, all your data on W, this one, for the class 1 and for class 2. Same way here. I'm just doing it again. Here you can do to find a maximum for it, or yeah, because here, for example, just an idea. Look at this is my main equation, right? Yes. I choose to do S minus 1, but can you do different way? Can I multiply the both sides by B minus 1? What will be here? W equals to what, please? So what does it mean? W is the eigenvector for B minus 1S. Clear? For example, if I ask you in the midterm questions like this, example, like, let me do it here, like something like this. 2 is eigenvalue of S minus 1b, right? Find the eigenvalue of b minus 1s. How we do it? So we just the transpose, right?
Yes.
How to find it here? Just go to the definitions of the eigenvalue and eigen. Can you try? I give you one minute, please. If you don't give correct answer, I will put it in the midterm. Please try. So what does it mean? You have to find a real value, right? Something looks like 2. Okay, I will do it, but later. Look here, please. when you are not able to, you don't know how to start, what do you need to do, please? For any time when you have difficult questions, how you will proceed to solving the questions? No, in general, how you do? When you have difficult questions, how to start? Go to the definition, right? Always definition from there, it's right. What is definition here of eigenvectors? So 2 is S minus. What does it mean? Mean S minus 1b. If I multiply it by eigenvector, it's giving me 2, this one. Are you okay with that? This is definition, right? 2 is given, eigenvector is anyone. I don't need it, right? The question about this. So now, what I need to do, I need to inverse. How to remove S here, please? You multiply by S. What will be here? BV. 2 is constant, I can take it outside. What will be here? S. I want to get rid of B minus. Why? Because I need to get this shape. I have to do change to reach this shape. What we do now? Multiply the both sides by B minus 1. What will be here? V equals to 2, B minus 1, V. So 2, take it outside, what will be here? 1 out of 2. So my matrix, this is S, sorry. Multiply by A by V, I get this one. So the new eigenvalue is half. That's it, finished. So you see, start always by definitions, trying to change your definition to look like the questions, and you find the answer. Clear? So in general, if you want to maximize this or this, doesn't matter. At the end, you find the same idea. Another question, do you think they have the same eigenvector? Yes, because if the V is eigenvector for this, is also eigenvector for this one. It's only the matrix should be, the eigenvalue should be opposite. Okay, so now what you need to do, if you summarize, you have to calculate B, you have to calculate S. So what will be here? We have S and B. You need to calculate S minus 1. You multiply it by B to find eigenvector and eigenvalue. And that's it. Done. Look example here. I give you S and B and W. So here, if you guess what is your W, which direction is. So some questions in the midterm or final, I give you a plot like this. I say, please try to guess, to draw what is the principal vector for PCA or the W for LDA, for example. Here, how to sketch it roughly?
PCA is going to be.
PCA, let's do PCA. Good.
PCA is like this.
PCA should be this one, right? Excellent. What will be the LDA in this case?
This.
Something this one. Clear? So here, if you do x-axis, y-axis, there's always overlap. But if you take the W here, we do the projections, the blue and the red are separated. Clear? Here on y1 and y2, these are the separations here. Okay? Another idea here, if you want to, only for the two classes, we can do something quickly. And we don't need to do the inverse matrix and so on. So if it's two classes only, W is always equals to this formula. So what does it mean here? You find only S minus 1. Simple. You multiply it by mu1 minus mu2. You get your directions. Why I don't care about this? Because this is a value. I just need the direction, right? Because any vector is, what is the most important for us? Is the directions. Big or small, doesn't matter. Because later on, I have to change it to unit vector. So W is always like this. Equals to W divided by the norm. To make sure that is always unit vector. The proof is here. This is what you want. B is this one. And BW should be equals to lambda SW, as we did before. So look here, for example, from here to here, this should be equal to this. I just get the definition of B. By definition of B is this. This times this, what is it? Value or vector here, please? This one here. It is vector or value.
Vector.
Are you sure?
No, it's scalar.
No, it's value. Because mu1 and mu2 like this, when you do the transpose became rho. Rho colon is a value. So this is, please, this is a value, and this is a value. So it will be at the end, SW, it is parallel to mu1 minus mu2. We have this one. And we are done. So this is just shortcut for calculation, but only when we have two classes. It is not general one. Okay? For example, here, if I give you s minus 1, and they ask you how to find a w, s minus 1, you multiply it by mu1 minus mu2, you get this value, but later on you have to force it to be a unit vector. Okay, so direct calculation is easy, but just I give you the proofs how to do the derivative to refresh your memory about the class 0. Okay? Now, what happens if we have, this is another example, class 1, 5 samples, class 2, 6 samples, this one, we have C1 and C2, and here if I ask you, if you want to do the PCA, it will be this direction, right? Right? Because we're looking for the large values. So do you think PCA, we can apply it for classification here? No. Okay. Okay, so the same thing as we did before, I'm just doing another way. So what we have, we calculate the mean, we calculate S, you do, so here for example, we don't need to calculate the B, matrix B, in two classes. Just calculate the S minus 1, you multiply it by mu1 minus mu2, and you get your vector W. If you get your vector W, what we need to do? Project all your data on W. Clear? And we know how to do the projection, right? WT times your matrix. Here, we can do it here. We have all the projections here, and we can do. For example, here, questions here. Do you think we can do the projection on the red one or the green one? Which one is more correct? The projections.
Green.
Hmm? Doesn't matter, yes, because looking for the direction. Thank you. Exactly. Doesn't matter. Because at the end it's same directions. We don't need we do it up or down. Look here, when you do the projections, you push it up or down, we have the same behavior, right, of the data. It doesn't matter. Here, you see for example here, two ellipses here, when we do projection in this case. So do you think this one is the best one? Or we can find better?
No, this is the best.
I think the best one. Here,
Also,
can you find better?
no.
Because if I take this one here, the green one will be merged with totally with the red one, right? Yes? So we can classify the red one almost correctly, but the green one is gone. But anyway, if I do this one here, I can say this is the green and this is the red one. So it will be the misclassification will be only this is the red one. But still okay. But if you do this one here, it will be, yeah, you have to find out.
I think it's the same because the misclassification will be the same area, whereas they intersect.
Yeah.
Even if we do it like this, it will be the red one will be fully classified properly, but the green one will be also misclassified with the intersection.
Yeah, so it is about how to minimize, but according to the calculation, this is the best one. But here,
The rest.
No.
I think it's good, right? It is separated or not at the end. Can we find better?
Yes.
Which one? This one like this?
Yes.
No.
I think if you do this one like this, for example,
It will be intersection with the red one.
I think you can find a lot there, but it tells just how to minimize those small points here. This one here, I think yes. I'm just giving some visualization. This case is here. Whatever you do, there is always overlapping. So what does that mean? LDA is not suitable in this specific examples, right? Because it's totally merging. So what does that mean here? Mean more you need more features, or this feature is not related to it is not relevant to do the classification.
There is no any tool that can classify this properly. I mean, it's intersecting in most.
There's a lot of overlapping, yeah. Whatever you do, there's overlap. So either we have to move to kernel LDA. We do it later. Now, what happens if you have 3? The same idea, right? But in 3, okay, the variance should be small for each one. But how to M1, M2, M3? Before we have M1 and M2, right? We do different square should be maximum. How you do it here?
Maximize
We
the mean between each.
maximize the distance between M1 and M2, and then M1 and M3, and M2 and M3. Like
But you will make your function very complex. Another one. An idea? Try to think before giving the solutions. You have M1, M2, M3, right? And you want to measure should be far to each other. Everyone should be each
So
other.
the pairs, each pair.
Well,
M0 minus M2, M minus M1, M1 minus M2.
yeah, but we imagine if you have 5, in your case,
Similar, yeah.
2, 5. 2 out of 5. Conversion is a lot. Yeah. Okay, what we said about the variance. Imagine you have M1, M2, M3, M4 are here, right? What you want? We want them to be far to each other. What does it mean? They are not consistent. So it means the variance of the means should be bigger. Clear the idea? So here, if we do the projection here, if we do the projection here, what you want? We want everyone has a small variance, right? To be tight. And M1, M2, M3 should be far to each other, right? So if you do a minimum distance or you add more variables, you make things difficult in optimizations. So think about optimization. So the easy way, what we said, M1, M2, M3, M4, in order to be not consistent, mean far to each other, their variance should be a bigger. As simple as that. Clear? Yes? So what that means? The variance, we need a total minimum is here. Mi minus the total minimum square should be a maximum. And the variance for each one should be a minimum. And we do the ratio again. Yes?
Isn't it the same? But if we can say this, we can say this. If we focus on minimizing the variance of each class, like this is the main goal, because if we do it, as you said, M1 minus it will be endless.
But if you minimize the variance, but maybe they are M1 and M2 are the same thing. So whatever you minimize, there is always totally overlap.
What is M here?
M is the mean of the data, but on y-axis. Now, for example here, this is your data, right? Take the blue one. This is your data, right? The mean here is mu3. The mu3, when you do the projection, you get M3. So M3, it is the mean of the projected data on W, over W. You got it?
Yeah, but what is M?
M here,
M, because we are subtracting M1 minus MI minus M.
yeah, here, Mi, it is I going from 1 to number of classes. For example, here, M1 minus M square, M2 minus M square. So M1, M2, M3, they are the mean of each cluster.
So what is M?
And M, it is the total mean. And N,
The sum of the.
You mean to say, can we replace M with another factor? Can we use instead M of another symbol?
you can, yeah, of course, yeah, doesn't matter.
Because
No, I think she's asking what is M. Is it the sum of means? Is it the sum of means?
It's the mean of the data.
Yeah. Okay, yes, okay. How to find, okay, if I give you M1, M2, M3, how you will get M? But how to get it? How to get it? No, I give you only examples, okay? You have N1 is 10, N2 is 20, N3 is 20, M1 for example here is 2.5, M2 is 5, M3 is 2, like that, okay? Questions here, find M.
So, MI divided by.
So it will be M1 plus M2 plus M3. No.
The numbers are different.
So what is M? M is the size, the sum of all, right? Yes, sir. This is class 1, this is class 2, This is class 3 divided by
All possible outcomes.
n, right or no? What is this one here, please? This one. This is m1 times
Times n.
n1 times m1. Do you okay with that? Because m1 is the sum of this one divided by n1. So at the end, what is n, please? We call it a weighted average. You can do it. It will be n1 times m1 plus n2 times m2 plus n3 divided by n, what is n1 plus n2 plus n3, which is the total mean regardless the label. Okay, so with this we call it average weighted. Okay, but it comes, you see it comes from simple idea. The mean is this plus this plus this. This is n1 m1, n2 m2, n3 m3, and you get the plus n1 plus n2 plus n3.
So the center, all of them.
Often, yes.
From the graph, it looks like it's just.
Yeah, for example, you see here, mu1, mu2, mu3, the mean of each class. The mean total is mu. Their projection on W, you get M1, M2, M3, and M.
Doctor, my question is this symbol is confusing because there is another concept in statistics, moments. In moments we mostly use M1, M2,
Yes.
M3, M4.
Yeah. But later on, we use only S and B. We don't use M at the end, later on.
Sir, I think I understand it now, but for example, if we maximize the distance between M2 and M, it makes sense because I'm pushing the M to the maximum like distance.
Yeah.
But if I do it for M1 minus M and M3 minus M, it's like I'm just shifting M3 and M1 next to each other.
I agree with you.
If I do it M,
I agree with you. It doesn't work all the time. I agree with you. Yeah, I agree with you totally. Because when the variance is bigger, maybe M1 and M2 are the same, but the other one is too far.
Yes.
Yeah, of course. Yeah, I know. This is just a way how to simplify it. Yeah, but it is not all the time. Yeah, I agree with you totally. So this is why we use all the combination, but it became difficult in the optimizations. So we think to make it easier for the next step. Okay, so now we do the same thing as before. We calculate B by you see here, the mean minus the total mean. The matrix 1, matrix 2, 3. For K matrices, we add them. We add also the covariance matrix. So we have B and S. We inject them in our things and we get the same idea, same calculation. The only difference here is B and S is multi-class. So at the end, you have to find S minus 1B eigenvalue and eigenvector. Okay? But here there is no shortcut. As we did before, in 2 classes, it's enough to calculate S minus 1. You multiply it by mu1 minus mu2 to get W. But here, you have to do this process. Okay, the idea here? So, of course, there is always drawback for this one. It is not perfect. It's still under research. We can do better, how to combine, still always. So here, how to make it easy way. Here there is typo. Can you tell me what is the typo here? In the last 2 lines. What we want to do? Maximize J or minimize J? So is just here, be careful about it, okay? So be a maximum, not a minimum. Okay? Now there is sometimes when you do the calculations to hit technical side. S minus 1, you cannot find it. What does it mean? It doesn't have inverse things. How we can solve this issue? We go to the PCA, different one, right? And do, you remember PCA, we do UR, right? The R directions, or the R biggest eigenvectors, eigenvalue. So we do another space, and we apply the same idea, okay? So we have X and Y, or you give to Y1 and Y2, which is the eigenvectors. So just an idea here. Again now, how to do it? Okay, let's summarize all the points until now. How to find W. First of all, so all the summary, what we are doing. First of all, you have your data. What does it mean this XILI? What does it mean? mean the data is supervised. We have a class label. Clear. How many classes do we have here? How many classes? K. Okay. What is the size of each class from the second line? N, I. If class 1 N1, class 2 N2, until N, K. Clear? Any value. So first of all, what we need to do? Find the mean of each class is here. We call it X bar. So what need to find? Matrix B. What is matrix B? Between classes. So mu minus the total mean square, and we want to maximize it. Clear? Second one, we have to find the variance to minimize. The variance mean covariance matrix for class 1 plus class 2 plus class 3. What we want to do in this case here? To minimize or maximize? Minimize. So within the class. Of course, before doing the covariance matrix, what we need to do? Center your data, right? Remember, right? And PCA. How to center the data? Any class J, you have to subtract the mean of the class to make a center. And the product is your covariance matrix. Done. We have B, we have S. What we need to do? You have to find S minus 1B, the matrix, find the eigenvalue and eigenvector, take the biggest eigenvalue corresponding to the biggest eigenvalue. You get your direction W. When you get your direction W, you do your projections for the entire data, class 1, class 2, class 3. They are in the new line. Keep the same label. It will be easy for you to do the classification. Clear? So all what we did here, why, how, derivative is what we did. But the most important for me is this slide. Clear? An idea here. If it doesn't work, can you propose me another idea? For example, just before the slide, a circle over another ellipse. You cannot find. We do whatever direction, all the 180. How many directions we have? How many directions we have? Vectors. Or how many angles? From 0 to 360?
360.
Yes? We can do less. Because only from 0 to
180.
180. Because anything is similar, right? Doesn't matter, okay? Why we use 360? Just question out of topics. 360, it is not angles. The measure of the angle of 360 does not exist mathematically. Who can tell why the people they use 360?
Because in the beginning it was given as 360 degree.
But why 360?
For easier visualization.
Okay, but why? Yes, it is for easy to evaluate for human, but why? The origin is the moon or the earth turning around the sun in 365 days. So just to approximate it, to be lazy, they call it 360. But all, nothing else. So it is not mathematical, okay? Just as extra information. So here you have to put a transpose. Why? Because it will be mu according to the size. Okay, so I explained everything in other way, so you can check it later on, or what I'm doing to split the data to understand what we are doing. Okay. I will do 2 minutes after taking the break. Okay, so now if it doesn't work, what we need to do? As we did in PCA. Kernel fit. Why would this mean kernel? We go to another space. Why we do another space? Can be rich space. We can get better. So how to do any vector can be written as linear combination of this one, right? So this comes from linear algebra. So if you have a lot, look at vector, 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 vector. Every vector can be written in a basis. Yes or no? So the same idea, if we do this linear combination of all the vectors, I can find any vector in the span, we call it a span spaces. Do you idea about vector space, linear algebra? So to understand why, just go a little bit what does mean. Okay? So anyway, we are now in a new space. What we call it? Phi x1, phi x2, until phi xn, right? So it's the same thing as we did before, just think always we are in the new space, but we don't have explicitly the functions, but we need to use a kernel. What is the kernel? Is the dot product in the new feature space. The dot product in this we call it kernel, and kernel is given to you. Can be Gaussian, can be polynomial, can be anything else. And everything, what we did is the same thing. Okay? Just we have to deal with not phi, only k, the kernel. This is only the trick that we need to do. Okay, look for example here. I have my W. I'm looking for it. So what is it? I need to find to this one. Here, for example, here, one first thing you need to do, simplify the notations. Okay, I have my x1 until xn. The size here is n, the size here is n, number of features. We go to kernel, which is our matrix, phi x1 until phi of xn. What is the size here? N. The size here is something bigger than n, okay? So now, okay, if I say W equals to the sum of this one, right? From I equals to 1 until n. I want to write it as matrix product. How we can do it? This one is exactly the same thing. Times alpha 1 until alpha n. So what should be at the end? We call it so when you put capital X means a matrix. When you put small x1, x2 means a vector. Times alpha. Alpha is this one, okay? Clear? This is my W. If you want to do a projection, any data or any vector, for example here, what is the projection, please? Like this. Projection of phi xi over W. What is it, please? The formula is WT times phi x. What is WT, please? Tell me, according to the names here. Alpha T phi x, this one, right? Times. Okay. What is this one here, please? Phi of x1t until. Yes? Times. Clear, right? This times this, what is it? Kernel, thank you. So it will be here, alpha. What will be kernel? x1, xi. Here kernel, kernel, x2, xi. Until the last one, kernel of x and xi. What is this one here, please? Is the kernel of the kernel matrix of the I. So we write it nicely. Alpha T K I. It is kernel. To make it easier, the way how to simplify notations, okay? So at the end, we can write all those techniques things. Okay, so you have the kernel matrix, I and J, and it is symmetric. So it is just kernel product. What does mean this one here, please? Phi xi dot product with phi xj. That's all. Okay. Beta. What is beta here? Is the projections. Beta is the coefficients of the projection on the entire of the x vector on W, which is this one here. And this is the way in these equations, but I prefer to use this one is much better to simplify. Is alpha t with j. So here again, I have to calculate the mean, and the covariance matrix, and the covariance matrix is always related to 2K. So let me give break and we finish this one and we can stop, okay?
Doctor, the midterm is up to which chapter?
The midterm is 25, right? October, right? Yeah.
You already specified this up to the ECA.
I think, can we include it's up to you. Can we include SVD until SVD stop? Last time? So please, can you which topic will be included in the midterm? If it's not included in midterm, it will be included in the final, up to you. So do you want to stop until kernel PCA? Or we include the SVD? Kernel PCA, okay.
Doctor, the midterm material is not included in the final.
Huh?
The midterm material is not included in the finals.
Most likely I would focus more on the last one.
Free.